Okay. Yep, that's good. Okay. Rag. All right, we'll look at chapter 14 first. Let's see. All right, number 1 in the review. That's a good place to start because that gives us a place to start with definitions. So, let's look at the 1A. And the question is, which of the following is a conjugate acid-base pair? So let's take, A does have an acid there at the beginning. So we're going to take that acid. Okay. And what does it do in water? Right, so when we put it in water, it's going to react with any water molecules that are there. Talking makes it worse. And this is going to be the acid. And water, remember, is amphoteric. It can be acid or base. So this is going to be our base, which means the base gives up a proton, accepts a proton, and the acid gives up a proton. So if this gives up a proton, it's just going to leave the chloride ion. And that proton ends up on water as the hydronium ion. Right? So when an acid loses the proton, it becomes its conjugate base. So this would be the conjugate base of that acid. Okay? And that makes this the conjugate acid of that base. Okay. So when the question says, what are conjugate acid-base pairs? This is the acid, and that's its base pair. And all that's required is for the acid to lose one proton. So the conjugate acid-base pair for A should be this and that. But it's not the way the question is. The answer is given as this and this. It can't be that. Because you can't add a proton to that and get this. Okay. So that one's false. And we can do the same thing with the rest of them. We'll just take them one at a time. So for B, we start with the acid here. So what would its conjugate base be? Right? It's got 2 available protons, but the acid-base pair is only 1 proton different. Okay? So the conjugate base of this acid is just 1 proton missing. Right? Is that the one they give us? Nope. See, they stripped off 2 protons for B. So that makes B false because they set it up as this. Okay, let's look at C. They're saying that this is the acid and this is the conjugate base. I'm sorry? Yes, because if you add a proton to that, you get this. Well, that one's true. And since E says more than one of these, we got to go through all of them and check them out. So how about this one? D. So if we have the hydronium ion as the acid, and they're saying this is the base pair, if you add one proton to that, you just get water. You have to add two. You have two protons to this to get that. So that makes this false also. So that means E is also false. So that's why C is the answer to that one. We don't often think of ammonia as an acid, but when it's set up correctly as acid conjugate base pair, it satisfies the definition. Okay, that was one, and we are recording. Did you have any trouble viewing my recordings?
On Blackboard, I did not. I didn't look at it.
That's okay, because the first attempt that Sarah, right?
Yes.
Okay. First attempt that Sarah made, she couldn't see them. So, and I was looking through there, and I said, because I went in to look at it myself, and I couldn't call them up from within Blackboard. So then that's when I went to investigate and see. Turns out that if you make them private, you got to say who has access.
Oh.
Right? So I changed them all to public, and you should be able to get to them now. Plus, if you see me wince and drink some of this, that's because I have a bad toothache here.
Oh, ouch.
And for some reason, hot makes it worse and cold makes it better.
Mm-hmm.
Okay, so that was one, and that was a good one because it gave us the definition of acid-base pair. Let's see. Okay, number two is sort of an extension of that. Let's see if we learned anything from one. Okay, hydrogen sulfate, or bisulfate is the trivial name, is HSO4 minus. HSO4 minus. Okay. It can act as either an acid or a base. In which of the following equations does HSO4 minus act as an acid? And so if it's an acid, it has to give up one proton, doesn't it? So if it gives up that proton, that gives you that as your conjugate base, and this as the conjugate acid of water. All right, so let's see which one matches. And let's see. It has to react with water. And A can't possibly be it. Because if it accepts a proton to be H2SO4, it's acting as a base and not an acid. So B says that it reacts with hydronium.
How does it go from just a negative charge to, oh, never mind, sorry. Never mind, just.
It balances, yeah.
Yeah.
So the one that looks like the one we drew up here is D. HSO4 minus plus water yields SO4 2 minus plus the hydronium. So that would be D. Okay, I'll just leave that up there. We need to look at 3, maybe. Which of the following is the equilibrium constant expression for the dissociation of HOCl? That's a good one. Dissociation constant for HOCl. All right. If this is in aqueous solution and it reacts with water, actually this should be liquid. So water can't be a solution in itself. So that's a pure liquid. And this is going to transfer 1 proton to water and leave that ion. Okay, so now we can write the equilibrium expression for this as the products. Since there are no coefficients, and let's be sure, should there be 1, 1, 1? No, that's fine. All coefficients are 1. And that's typical for acid-base reactions because you're only moving 1 proton at a time. And then we need our hydroniums divided by, okay? Now why don't I put water in there?
You said when it's pure liquid, it doesn't go in there.
Yes. So that's the expression for our dissociation constant for HOCl. Let's see, can we name this one? Well, let's see. That's the chlorate. That's the chlorite. That's the hypochlorite. So this is
Hypochloric acid?
yes.
I was getting there. You're just a step ahead of me. So, on that,
So that's 3. Let's see. They seem to be progressing fairly well, logically from one to the next. I don't always do that, but maybe I got lucky on this one.
no,
You got a question on that one?
So what would be the
so the answer is not what we have here on the sheet, so I guess the answer is none of these.
Oh, no. Okay, I should make that point. This is the true reaction in solution.
Okay.
But another way that you'll often see it written is just the acid dissociating to this plus this. Okay, all we've done there is remove the water. Right? We're taking the water out of here. We're taking the water out of here and leaves only the proton. So then, actually these expressions are equivalent. Then you would have this one and that one divided by this one. Okay? Unfortunately, that's just the way this chemistry is developed. So either one of these, this one is equivalent to that one. And the K value for this one is identical to the K for that one. I suppose the key word there is dissociation. a dissociation constant for this acid. When you dissociate, you don't react with anything, you just break it apart. So it breaks apart into this and this.
Adding the water was assuming there was just a vessel for the reaction to occur.
Actually,
Or
this is it's like a simplified version. If you look at water as a spectator, then it disappears from this side and it disappears from here, leaving only a proton. Okay. Let's see. Number 4 requires a little calculation, I think. So I better make room for it. So 4 says, which of the following is not true for a solution at 25 degrees that has hydroxide concentration of 2.5? Hydroxide concentration of 2.5 times 10 to the minus 6 molar. All right. So A, is this true? You don't even need to know that to answer this one. That one's always true. KW is always 1 times 10 to the minus 14 at 25 degrees.
that's the constant for water, correct?
Yes, equilibrium constant for water. And you would just have this and that. Okay, so that one's true. B, the solution is acidic. The only way to know that is to find out what the pH is. Okay. So we need to do negative log of 10 to the minus 6th. That'll give us the pOH. Calculator. Okay. That would be 5.60 pOH. So the pH is equal to 14 minus that.
Okay, why did you use the negative log?
That's the definition. Anytime you calculate P something, you take the negative log of it.
The negative log concentration.
Yes.
So isn't so I thought that amount was supposed to be the hydrogen ions, the concentration of hydrogen ions.
Yeah. Oh, wait a minute. You might be, no, let me see.
pH equals the negative log times the concentration of hydrogen ions.
Right, we're doing pOH first because this is the hydroxide concentration.
Right.
So I do this and that gives me pOH. Then pH is 14 minus that. Remember, pH plus pOH equals pKa by pKw. Okay. So since this is 14, right, take the negative log of this, you get 14. It's always equal to this plus that. So if you know this one, subtract it from that one and you get that one. So pH is 8.4. That is not acidic. We've already calculated it, so C is solution is basic. That's true. It's greater than 7, so it's basic. D, the hydrogen ion concentration is 4 times 10 to the minus 9.
You just do log of 8.4.
What's that? Yes. You take the anti-log of 8.4. Of the negative. The anti-log of, so this should be 10 to the minus 8.4. This is what they're saying. This is reality. So we check the 8.4, change the sign, and then do 10 to the power is 3.98 times 10 to the minus 10. 9, excuse me, 10 to the minus 9. That was true. And do we have an E? The KW is independent of what the solution contains. That is true. KW is always 10 to the minus 14. So B is the only one that's false. Questions?
I gave myself spring break, so I
Oh,
haven't thought about chemistry in a week.
I see.
Yeah, unfortunately, I didn't either, so I
So
was laying in bed last night, I was like, a second. Hold on, or right out.
I just, so, none of that. No, I'm gonna need to review.
I've already got, last night I opened up all the different videos and tabs, so I can just go through them this week.
Let's see.
Just goes to show you, you can't take a day off.
No, I learned that a long time ago. I was here every day. Same time, same station. Except for Logan, I had to drive down there. Because their spring break's not till Easter.
Weird. Especially since it's one school. You can do it all at the same time.
Well, I think they're trying to coordinate their spring break with the public schools. They have an Easter break. Okay. Well, let's try to find the problems that cover the fundamentals at least, and then we'll go back and look at some of the oddballs if we have time. All right, on the tails of 4, we'll look at 6. If the POH is 12.1, what can we say about it?
Very acidic.
Exactly right. Because pH equals 14 minus 12.1 is equal to 1.9. So it's very acidic, which is 8.
What would be defined as slightly acidic? Would be anything between 4 and 7, or?
Slightly acidic. Judgment call. It's like maybe, yeah, 4 to 7 would be right.
So the higher the OH number,
Because in the 4 range is vinegar.
so if the higher the OH number, the more acidic it is.
Yes,
Okay.
exactly. Mhm.
And the lower the hydrogen ion number is
More acidic.
more acidic.
Yes. That's
So
exactly
would
right.
you qualify that 12.1 as very acidic then?
Oh, definitely.
Okay.
Yeah, because the pH here is 1.9. You're getting down in the stomach acid region. Okay, that was 6. How about 8? So for 8, we're going to be interpreting acid strength based on their Ka values.
Ka being defined as?
The dissociation constant for the acid. So if you say, let's see, not that one first, let's do that. If you have an acid and it dissociates into that, then the Ka is going to be like that. So that means that for the, to answer 8, the strongest acid is going to be the one with the largest Ka because it produces a larger numerator, right?
Which would be E.
Right. When you're talking about strength of an acid, concentration doesn't matter.
It's just Ka.
It's only the Ka. So for HCN, we have 6.2 times 10 to the minus 10. For H2C6H6O6. What that is? The first K, because some of them, notice that B, you have 2 protons available. Notice how they separate the protons. They put 2 hydrogens at the beginning, and then there's 6 hydrogens inside the molecule. Those do not dissociate. They're locked in place. So the first one is 7.9 times 10 to the minus 5. And the second one is 6 times 10 to the minus 12. Then we have HC2H3O2. That's acetic acid. Is 1.8 times 10 to the minus 5. You're going to prove that today in lab. And this one is 3.5 times 10 to the minus 8. And the last one, HF, 7.2 times 10 to the minus 4. So one thing to recognize is when you have two available protons, the only K that really matters to the pH of the solution is the first one. Because look what happens between the first and the second one. 7 orders of magnitude difference. So the second one doesn't mean a thing. It does not contribute to the pH. So we just focus on the first ones. And the largest one, like you said, the largest one determines the acid strength. So we see -10, -5, -5, -8, -4. HF is the strongest acid in that group. I mean, even though it's a weak acid, it's still the strongest.
Out of those.
Yes. And that's just the acidic character of hydrofluoric. It also has some chemistry involved that make it even worse than its acidity. If you drop concentrated HF on your hand, just let it sit there. It'll eat all the way through your hand before it's done.
Can we just do it maybe slower than hydrochloric acid would?
It might be slower, yeah. But the fluoride reacts. It's almost, I can't say it's catalytic, but it behaves like a catalyst because it just keeps going. Especially when it gets to bone. Calcium fluoride is soluble. It solubilizes your bones as it goes through. It's nasty.
Meaning you would like turn your bone to dust, basically?
No, not dust. It would solubilize it.
Exactly what that means. It would just become.
Puts it in solution.
Yeah, it would just go in
Right.
solution.
So whenever I used to work with it, I had a double glove. Wear protection. It was bad. The only reason we used it was when we digested, particularly when we digested soil samples, we needed the fluoride to solubilize some of those minerals. It was very good for aluminum, calcium, even magnesium. We could get the entire sample in solution if we had fluoride. And,
And we drink that
oh, sodium fluoride?
in water.
Yes. And you have it in your toothpaste, but it's very, very low concentration. Plus, it's not the acidic form.
That's the acidic form that makes sense.
Yeah, it's the salt that we put in our water and in our toothpaste.
Should we just briefly cover number 5?
Yeah, sure.
Because that would be a little bit of a refresher. I'm pretty sure it's like a strong acid makes a weak base, but
Okay. For 5.
you may not want to write that now. It's a lot of writing.
Oh, yeah. Okay, so let's check the question. HA and HB are both weak acids. So we just put that much. These are conditions. HA and HB are weak acids. How are they related to one another? HA is a stronger acid than HB. So we'll just use that as our expression. So which of the following statements is correct? A minus is stronger base than B minus. So the rule is, if that's a stronger acid than this one, then the conjugate base is a stronger base. Right?
So it's not A.
So it's not A, that's right. So A is out. B minus is stronger base than A minus. That part is true. Which is stronger than H2O.
So would B minus be a stronger base than H2O, or A minus, would A minus be a stronger base than H2O?
I'm gonna follow my own logic here. Okay. For weak acids, the conjugate base tends to be stronger than water as a base. So these would be stronger than water.
Would they be stronger than chloride?
No, because HCl is a very strong acid.
Which would produce a very, very weak base.
Right. Oh, yes, so they would be stronger. That's true.
Is it stronger than water, chloride, as a base?
Mm-hmm.
So it would be BA chloride water.
Oh, no, I'm sorry. This is the weakest base of the bunch.
Even weaker than water.
Yes, even weaker than water.
So it's B.
Yeah, so B makes more sense. B, of course, which of the following statements is correct? So the selections you have says basically there's only one that could be correct. Because if E is correct, then none of them are. So we can stop at B.
Okay, can you, when you just throw chloride in there, we're just supposed to know that chloride, okay, when it's written like that, chloride negative, we assume that a proton was given up,
Yes.
making it a base.
Right.
But how do you know it's weaker than water as a base?
Because hydrochloric acid is a strong acid, which makes it a stronger acid than water, which also makes the chloride a weaker base than water. I can take a break. I've been drinking too much of that.
Fair enough.
I really haven't looked at anything chemistry
I haven't
since
either.
the last class.
And I'm regretting it. I was like, I'm gonna do it Saturday, I'm gonna do it Sunday.
No, I actually gave myself last Monday off. And then, work, and the other day off I had was errand, and I didn't take it. I worked at errands, so.
Yeah, I'm not looking.
I just drove 10 hours in the last, well, more than that, because I drove back here today, but.
I have not done a single thing with this lab report.
Nope, we had, I don't know, everyone said something about proving the acetic acid, something, with a K.
So we just have to write out all of this. So many lines.
I did not finish that yet.
I haven't even touched it. I was kind of hoping to do next week, but then I found that we had a chemistry lab this week, so I was like, oh, that's pretty good. Fantastic.
Did you have an appointment with your dentist?
I called this morning. They're trying to fit me in, but I got to call back. They got to call me back. What he may do is, if he can't get me in today, is call some kind of prescription in for the pain. I know when I was growing up, all we had was Aspirin. You lay the aspirin right on your tooth and let it dissolve.
Oh, boy.
Oh, it tastes wonderful.
That's like whenever I was a kid and I had a cold sore on the inside of my lip, and I was like, put some alum on it.
Somewhat.
Alum, it's like a.
Alum, yes. Uh-huh.
It burned like fire and tasted horrible.
Uh-huh.
But it worked.
Yeah.
I don't know if it was worth it, but it worked.
Right. Okay. So B was the answer to that one. Let's see. Maybe we gotta look at 9 also. Let's see, that's 8. There's 9. Okay. Which of the following statements is true? pH of a strong acid is always lower than the pH of a weak acid. It's always lower than pH of a weak acid. Is that true or false?
That's your name.
Think about what we mean by strong and weak. Strong and weak only refers to the Ka. How much does it dissociate? It is possible to, and this is that's a intensity factor, is the K. In other words, it doesn't matter how much you have.
So the pH of hydrofluoric acid might be lower than the pH of hydrofluoric acid.
You could make the pH of HF greater than HCl. When you talk about the pH, you're talking about capacity factor. That is, it does matter how much there is. So if this weak acid only dissociates, I don't know, 10 to the minus 5, and the strong acid, of course, doesn't have K because it's completely dissociated. If you make this one, if you make the concentration low enough, and this one high enough, you can exceed the pH. I got that backwards. Oh, no, I did have it right. The pH of a strong acid is always less than. No, strong acid can be greater than
Well, which number are we talking about? Because
9.
No. The number of the value of pH or the K value. Because the K
Okay.
value, that number technically is getting larger.
Right.
The pH number is technically getting smaller. So
This K is greater than this K. Right.
and the way the question's worded, I thought we were talking about the pH number, which would get smaller.
The pH of a strong acid is always, no, it's not always lower. pH of a strong acid actually is usually higher, but it doesn't have to be. But the way the question is worded, the answer is worded, the pH of a strong acid is always lower. No, it's not always lower. It's not always higher either. So that question is false no matter which way you put it. Does that make sense? It depends on the Ka and the concentration when you're talking about pH. So that was false. The pH of the solution can never be negative. Is that true?
Yeah. But the scale when it went to 0.
The practical scale. But the actual calculation? What if we say, all right, so the negative log of 10 to the minus 1 would be what? It'd be 1, right? Okay. What if your concentration was 1 molar? Okay. What's the negative log of 1 molar? Well, that's what? 10 to the 0?
Isn't that 1? Or I think 0 is 1 0.
Yeah, 10 to the 0 is 1. So the negative, see, power of 10, that equals 1. So the power of 10 has to be 0 to be equal to 1. Definitional log. So this is our pH. What if we just kept going and said, let's see, is that going to be right? No, that's not right. 10 to the first power. So if we had 10 molar, then that's possible. You can get 10 molar acid. Then the value would be minus 1.
Would that just be even more acidic?
Oh, yeah. It'd be extremely acidic. That's the type of thing you would get with concentrated acids.
Industrial farming applications.
So what we were talking about earlier, the scale running from 1 to 14, was just a practical use area. But the calculation itself can give you a negative pH. I mean, Sorensen didn't restrict it. He said, this is the math. It is what it is. So that was false.
Does that mean you can go up to 15? pH?
10.
Could it go up above 14?
Well, there's a practical limit, you know, because the molar concentration of water is I think it's in the 40s. So if you exceed the molar concentration of water, then you don't have any water anymore. So theoretically, it can go much higher. Okay, so C, for a conjugate acid-base pair, Ka equals 1 over Kb. Ka equals 1 over Kb. Is that true? We derived the formula for calculating Kb from Ka. It wasn't that. In order to calculate Kb, knowing Ka, you have to include Kw. Because Ka times Kb equals Kw. Which means that for Ka, that's equal to Kw divided by Kb.
So is that just the concentration of one acid and the concentration of another acid?
No. These are related because, let's look at it this way. Say you have an acid and reacts with water and produces that plus that. That will have a Ka. Okay? But if we add this part, the conjugate base, to water independent of the acid, say we add it as the salt, like that. Okay? Then it reacts with water. And sodium is a spectator. So what you end up with is actually sodium on this side and H. Yeah. HA plus OH. Let's see what we got. There's one there, one there, one there, one there. H2O, H2O. Okay, so that's right. This is Kb. Why? Because this reaction produces a hydroxyl, not a hydronium. Now, it's usually written simpler than that. That's a little complicated. It's usually written this way. Take that one, react with water, and it produces that. Okay, so we just take out the spectator. Okay, so that's the relationship between Ka and Kb. If you write Ka for the acid, then you take the conjugate base and use it as a reactant with water. And that reaction gives you the Kb. I don't think, we didn't get to this in class, I don't believe. I think I covered this in the videos.
So it's somewhere in the 6 hours of videos.
Yes.
Is it really 6 hours?
There are 2 2-hour and 30-minute ones. I think one's an hour and 40 minutes.
Oh my gosh.
Now the first one, you were here for that one.
Okay.
But the other two is like, what, maybe
The rest of-
3.5 hours?
The rest of chapter 14 and then chapter
And then 15, yes.
It's just, I think on the website, it's just acid base, part 1, part 2, and part 3.
Yes. You were here for part 1. But that's what's meant by Ka versus Kb. They're related, right? They're related through this anion here. Right, so that one comes over here, reacts with water, produces Kb. And I showed you how to derive this one from using Hess's law to combine these two. Right? Because if you combine these two together, you get Kw.
What do you mean combine them together? We
Add them together.
Just add them.
Mm-hmm. So if let's use this one and that one. Okay, so if we add them together, we get HA plus A minus plus 2 waters. And then this side you get horrible pain.
I would describe chemistry that way.
It definitely hurts
Yeah.
my brain
Yeah. Is it worse than a toothache?
sometimes.
Okay, then we have A minus here, plus HA, and then we have H3O plus O minus. Okay,
Toothache is finite. Chemistry is not so much.
is forever. So when we add these two together, we get this, and then we simplify it, of course. We've got A minus on both sides. We've got HA on both sides. We've got 2 waters. How did I get 2 waters? I added that one and that one. So 2 waters. So H3.
There's another H.
Yeah, that's right. But remember, another way to write this is to take the water out. So we take one of these waters out, one of those waters out. And it leaves us with this. Okay? See what I did?
Yeah.
Okay, so now the expression here, the equilibrium expression here is Kw.
Okay. I think you did go over that. Now that's ringing a bell.
And then if you use Hess's law, when we add these equations together, what happens to the K's? You multiply the K's. So Kw equals Ka times Kb. Okay? And that's where this came from.
1 times 10 to the negative 14. Concentration of,
Yes. So if you know one of these, you can find the other. If you know Ka, you can find Kb for the conjugate base. Right? It has to be for the conjugate base because Kb means a base reacting with water to give you a conjugate acid plus hydronium. I mean, not hydroxyl. That's the giveaway. The Kb produces hydroxyls. Let's see, we got through C. D.
so they're all false.
Yes, this is true.
Are logarithms learned in algebra, like algebra 2? Like,
Probably, yeah.
okay, yeah, it's been a long time. I actually did sit with a tutor that last week we had school and said, can you give me a lesson on logarithms?
Okay.
I guess it didn't help that much because I'm still like, okay, how do you do this again?
But for our purposes,
Yeah.
you only need one definition.
It's like, it's when I go to read the math sentence with it in it, it's still like a foreign language to me.
So when you say that, what you're actually saying is the definition says that 10 to the x equals A.
Okay.
That's it. That's all you need to know.
I'll just write that down and see if I can burn it in my brain.
That's not any useful information, is it?
I don't know.
It probably would pay to
Now,
memorize
if you
that.
put the negative in front of it, how do you read the sentence? You put negative log.
Oh, if you make a negative log for our pH,
Yeah.
then there.
Okay, so then that becomes 10 to the negative x powered equals A.
Yes.
Okay. Okay.
In case you have to go take pH and go backwards to concentration, that's how you would do it. Oh, there are some other rules for logarithms. For instance, the one that we use most often is if x times y equals something, then the log of x plus the log of y equals the log of A. So when you've got a product here, the log makes it a summation. And by the same token, if you've got x divided by y equals something, then it's the log of x minus the log of y equals the log of A. Okay? The basic log definition plus these manipulations are all you're going to need in chemistry. And that's good because that's about all I remember from logarithms. All right, let's see how we do on time.
Never enough of it.
Well, that's true. Quite true. 10:25. Okay. We could go over a little bit because the lab's not going to take long.
Oh, it's.
Now, I was saying we have until 10.
Okay. I was like, what?
Yeah, no, I did make the jump from daylights, from savings. Regular daylight. Actually, I didn't even feel it this year. I think because I get up so early anyway. Okay. Let's see. What? Anything else you want to cover?
Can we do 13?
13, okay. Let's see, which of the following is true about the pH of a solution of sulfuric acid? All right. pH of a solution, pH of sulfuric acid. Okay, what about A? If the solution is dilute, the pH cannot be calculated. Dilute. pH is unknown. True? True or false? As long as you know the concentration, you can calculate the pH, right? So that was false. It doesn't matter if it's dilute or concentrated. You can still calculate the pH. If the solution is dilute, the pH is completely controlled by the first dissociation. If dilute, pH is dependent on first dissociation.
Well, that seems partly true because you said earlier that the first dissociation was the one that mattered. But I don't know if it matters if it's diluted or not. Does that affect it?
No. Well, if it's concentrated, logic has it that yeah, first dissociation is it. But if it's dilute, it only depends on Ka1 because Ka2 is generally speaking much, much smaller than Ka1. And that's true. This is a strong acid, which means the first dissociation is complete. But the second one is a weak acid. So that one controls the pH. And I'm not sure if the lecture included, I think the lecture did include a calculation through various dissociations of phosphoric acid, where you have 3 protons.
I'm sure it just gets exponentially weaker.
Yes, yes it does.
So that one could be true.
Let's see. If the solution is dilute, pH is completely controlled by the first. Yes, that's true.
Good, since D and E are the same, and the whole thing was true.
Now wait a minute.
Oh, wait, okay. One of them is concentrated, the other one's dilute.
Complete solution. No, wait a minute. My work problem says that B is false, and I can't abide with that. Not anymore.
Got some aspirin dissolved in there?
Huh?
So you got some aspirin dissolved in there?
I wish I did. Dilute solution pH is controlled by both dissociations. I think I got that from the authors, and I find that hard to believe. I think B is true, which means we're going to have more than one true. Because if the solution E, if the solution is dilute, the pH is partially controlled by the second dissociation. Yay. All right, so if that one shows up on the exam, tell me about it and I'll give it to you.
Hopefully, we'll be one of those 10
Yeah.
Oh, we're pretty good.
Just a gimme.
That's the type of question that I hate anyway. Because you're supposed to logically work your way through the problem, and logic doesn't always work. I prefer numbers. You know, something you can calculate. That's why I hate those examples that show up on the slide where you have A, B, C's, and D's, and not real chemicals. I tend to skip those. Okay. Oh, okay, 12. Let's look at 12 rather than 13. Okay, did you have the same doubts that I did? Karen, about 13, since you asked about 13?
Yeah, because it was just the way you explained it before about,
It didn't jive, did it?
right.
Yeah. Okay, so we both had the same misgivings about that 13. So let's go back up to 12. I think 12, since it has actual numbers with it, will be easier to explain. So if you have a 0.1 molar diprotic acid, 0.1 molar diprotic, so it's got 2 protons available. All right, so they're called A, B, C, D, whatever.
That product's even associated twice.
Diprotic, it has 2 protons, right?
2 hydrogen.
Right, 2 hydrogens are available for dissociation.
Okay.
So A, the Ka1 is 10 to the minus 2 and K2 is 10 to the minus 7. So 10 to the minus 2 versus 10 to the minus 7. In which one would the second dissociation affect the pH significantly? Not this one.
So that's 5 powers.
They're 5 orders of magnitude apart. B is 10 to the minus 4 versus 10 to the minus 8. That's still too far apart. Right? 4 orders of magnitude is 10,000 times. C,
It's still 5 powers apart.
right, 10 to the minus 4, 10 to the minus 9. D, 10 to the minus 3, 10 to the minus 4. So that's only 10 times different. So that could conceivably affect this one could affect the pH. All right, so I guess that's why in 13 we said B was false. Because it's conditional upon what size is K2. The second dissociation never affects the pH significantly. Well, when you do the calculations, it turns out that this second dissociation will affect the pH. It may only affect it from maybe 0.1 or 0.2 pH units, but that's still significant because remember, pH is a logarithmic scale. So if your pH is different by 1 unit, that's 10 times. If it's different by maybe a fraction, it might be only twice, but it's still significant.
Carbonic
14, okay. Let's see, we have HOAC is the same as acetic acid. That's an abbreviation. And H2CO3 is carbonic acid. That's the form that carbon dioxide takes when you bubble it through your drink, carbonate your drink.
Carbonic acid.
Mm-hmm.
Interesting. Look at that portion of acid reflux.
Yes, but it's not the major problem, right? Because that's not the only acid in pop. The primary acid in pop is phosphoric acid. That's the one that dissolves a nail when you put it in Coke. Have you ever done that?
No.
Go try it. Just open a bottle of Coke and drop a nail in it. It might take a week, but eventually you pour it out and there's nothing there. It's gone. That's a reaction of iron with the phosphate ion.
So it would need to be an iron, not like a stainless steel.
Right. Stainless would present a problem because it would react on the surface and seal it and never get into it. You need a hard steel nail, not stainless.
So drinking Coke.
Not galvanized either.
Probably.
I'm sorry?
So drinking Coke every day is, how is that in the stomach?
Well, I've been doing it for years. I don't have an ulcer yet. I think it depends on your physiology.
And probably how much you drink of it. When I was a kid, I would get like a liter-sized cup just to fill it up.
Yeah.
A little bit different than drinking 12 ounces.
And of course, when you're talking about consuming foods and their effect on your physiology, it's a very complex subject because phosphoric acid, carbonic acid, they're not the only thing in Coke. Probably the major problem there is sugar. Yeah. You got sucrose and it's just going right into your system. So you probably get higher from the sugar than you do from the caffeine. Back to 14. Okay, which of the following 0.01 molar solutions has the highest pH? Okay. Okay, so acetic acid has a Ka of 1.8 times 10 to the minus 5. Okay, and carbonic acid has 2 Ks. 4.3 times 10 to the minus 7 and 5.6 times 10 to the minus 11. Okay. First, these are 0.01 molar, both of them. Okay. So we are comparing apples and apples. They're at the same concentration. So we can focus on the Kas to determine relative pH. First of all, is the Ka2 going to have any influence on the pH of carbonic acid?
According to 13 and 12, yeah, a little bit.
It's 4 orders of magnitude different. 10,000 times,
I was gonna say no.
no influence at all. If they were 1 unit apart, yeah, it would. So we can focus on this one versus this one. So the one that's going to dissociate the most, since they're the same concentration, this one's going to produce more hydrogen ions.
Because it's bigger.
Right, because that value is larger. So the acetic acid solution will be a higher pH. A lower pH, excuse me. So this one will be the highest pH.
Meaning it's more basic.
Yes. Leans, it's acidic, but it leans toward the basic. More so than acetic acid. Okay.
Wait.
So.
Let me see how, did I read that question correctly? Oh, I see, I went through. I didn't even finish the question. That just takes the acids. This is A, and this is D. So I didn't even finish it. This one is B. Wow. Must be the pain. It's affecting my brain. There's D. Here's E. Okay. So the highest pH, well, obviously, the acids are not going to give you a high pH. They're going to give you an acidic pH, right? Okay. So those two can be discounted. But we do have to consider the origin of these. Now, the rule of thumb is weak acid, strong base gives you basic solution, right? So weak acid, each one of these is derived from a weak acid and a strong base. So they're all going to be basic. Just the question is how much? How basic are they going to be? All right, so this one is going to produce that anion. So when it reacts with water, it's going to produce HOAC, acetic acid, plus hydroxyl. This one, since it's primarily controlled by, well, actually, we're looking at this one. So here we have right? And this one we've got HCO3 minus plus water yields H2CO3 plus OH. So in order to compare these, we need to look at the KBs for each one. Well, maybe we don't. What we have to do is decide which one of these is the strongest base. Right? So this one results from a stronger acid than either of these. So it's going to produce the weakest base. This is the weakest of bases because it comes from a stronger acid than that one. Is that clear? Okay, so we can throw this one out. It's not going to have the highest pH because it's the weakest base. And the reason it's the weakest base is it's the conjugate base of the strongest acid, right? This acid is stronger than either one of these dissociations, okay? So we need to concentrate on these two. Which one of these produces the strongest base, right? So if we look at CO3, 2 minus, that comes from here. That second dissociation produces CO3, 2 minus. The first dissociation produces HCO3 minus. Don't need to draw it. And this one is, let's take that one, Okay? So that's where these come from. If this is a stronger acid than that one, then this is a weaker base than that one. So this tells us that that one is the strongest base. So this one is going to produce the highest pH. What do we mean by strongest base? It has the strongest affinity for protons. Right. It has a stronger affinity for protons than does this one, which means it's going to shift more to that one than does this one. Okay, it's another way of explaining it. Now you could go in here and calculate the OH concentrations for every one of these reactions based upon these values, but you would have to produce the Kb for each one of these. And then do your ice table and calculate what exactly you have here. And you could prove it mathematically. But logically speaking, yeah.
And then, so this is the pen and paper version of, showing how, CO3 with a -2 charge has a stronger affinity for hydrogen protons. So, but in the real world, like, how often does it really play out like that? Like, is it?
Oh, in the real world?
Yeah, like just in this is chemistry in a laboratory setting, but
yes.
Like.
So this is, this is baking soda, sodium bicarbonate. Right. So you put that in solution, and it reacts with water to produce that. Or if you put it in there with another acid, it reacts to produce CO2 that makes your bread rise. Your quick bread rise. This one is sodium carbonate. Most people don't come into contact with this one because it's very corrosive. This is called soda lime. Okay. And we do use it in the laboratory because it has a higher neutralizing value than this one does. Right? Because it'll pick up 2 protons, whereas this one only picks up 1.
And what would you use it to neutralize?
We used to use it, we have acid baths for cleaning our glassware, and they're hydrochloric acid. I also had a nitric acid bath. And they would be sure that, they would assure you that your glass was completely free of mineral contaminants, because the acid would etch the minerals off of the surface of the glass. But over time, it loses its strength and loses its ability to perform, so you want to change out your acid bath. And then to do that, you don't just dump the acid down the drain. You neutralize it. So we would use sodium carbonate was the preferred neutralizing agent because
Base.
the carbonate, yes, the carbonate plus two hydrogens from the acid in the bath would give you H2CO3, and then actually what that would do is, this is not stable. It would dissociate into CO2 and water. It would produce a lot of bubbles, very frothy. But eventually, you check it with pH paper is the easiest way. And once you neutralized it, you could dump it down the drain. But it would take more of this than it would of that to do the same job.
So,
Good anecdote. Those things help my brain.
So we know that sodium carbonate is a very strong base.
Yes, it's the strongest of these three.
So it has the highest pH.
Yes. As long as they're the same concentration, it will give you the highest pH because of
We
this.
just have to infer that.
You infer it from the fact that this is the weakest acid reaction of all three. So that means it produces the strongest base of all three. Strongest base gives you the highest pH. Yeah, that's the way you infer it without actually calculating it. Put that out for laundry. Okay.
Oh, it's not good.
We're still in chapter 14.
Yep.
Let's see if we can, there are any other really major issues in 14, and we can get on to 15 and tackle some of those. Okay, the rest, it looks like they're comparing KAs. Oh, okay. About 36. This is a two-step problem. Because the question is, how much water should you add to 10 milliliters of 11.1 molar hydrochloric acid so that it has the same pH as 0.9 molar acetic acid? So if it's got to have the same pH as that acetic acid, you got to find out what the pH of acetic acid is first. Right? So if we've got 0.9 molar acetic acid, and the pKa is again 1.8 times 10 minus 5. Then we need to set up the reaction. That's going to produce this plus this. Okay? So the, let's see if I'm reading this correctly. Yes. We're establishing the concentration relative to this. So we know how much of this we're putting in. Then we got to say, how much does it dissociate to that one? So we've got a nice table that we have to deal with. So the initial concentration here is that. That's 0, that's 0. Well, we know that's not really 0 because water dissociates a little bit, but it's not significant. So the change, which way is it going to shift? That way, because that's 0. So that means we're going to lose, since they're all 1 to 1, we're going to add some here, add some there. Oops, sorry. Jumping the gun. Okay, so that's our equilibrium situation. And then the equilibrium expression for that is the Ka is equal to this one times this one divided by this one. Okay?
Well, it's not a quadratic formula that we got.
Yeah, so what we do is, since this is a very small number, we're going to say that x, at least in this term, is much smaller than 0.9. So we're going to say x squared over 0.9. And then solve it for, so I'm going to say that one times that one, and then take the square root of it. Right? So 1.8 times 10 to the minus 5, and 0.9 times that. I'll just do this. 1.62 times 10 to the minus 5 equals x squared. So that x equals the square root of that.
Wow.
4.02 times 10 to the minus 3, which is the hydrogen ion concentration. Right? So we don't have to go directly to pH yet. In fact, we don't have to go to pH at all, because we really want, what we really want is how much water should be added to uh, 10 milliliters of 11.1 molar HCl. Now, HCl is a strong acid, so it's going to be completely dissociated. All we need to know is we want the hydrogen ion concentration to be equal to that value. Right? So what we do is we set up the definition for the hydrogen ion concentration. Which needs to be that value. And then that needs to be moles per liter, right? So it's moles per volume in liters. So how many moles of HCl do we have there already? Right, because we're going to dilute it. And we're not going to change the number of moles of HCl. That's going to be the same. So the moles of HCl is going to be 11.1 molar times 0.010 liters. Right? That's the number of moles of hydrogen ions that we're going to have in that solution. So we just need to dilute it so that it gives us this concentration. So that means the volume is here. So the volume in that is going to be, you know what, we don't have to change. We don't have to change that to liters, because the numerator and the denominator are both going to be same volume. They'll cancel. So we can say 10 milliliters, and on the bottom, we're going to have 10 milliliters plus, well, let's not use X, let's use Y. Y milliliters that we add. Okay? Okay, so now we have an equation here in one unknown, and we can solve for it. So what do we have? Well, if we take this term and put it over here, we have 10 times that would be, actually, go over here? 4.02 times 10 to the minus 2 is this part times that, plus 4.02 times 10 to the minus 3 y. And that's equal to 11.1 times 10 would be 111, right? Right, 10 times this one. So now we can leave this one over here and divide this one into that one. Let's see. 111 and then 4.02 to divide. So that gives us 2.76 times 10 to the third. And y equals this one divided by that one. So I get, whoa, do I get that many? What did I do wrong? Or did I do wrong? No. Wait a minute, what's the answer in? The answer in liters or milliliters?
Meters is what you have here.
It's got two of them. It's got milliliters and liters. So maybe we should have kept that in liters. You think?
We could just convert it to liters, put it to both.
Yeah. But the answer I get is nothing like that. I probably made a math error. That's what's bugging me. Let's see if I set it up right. .1 molar times volume divided by 10. Okay, that appears to be set up correctly. Now, what did I do over here? This one times that one should be this one. This one times that one should be this one. Yeah. And that one is 10 times that, which would be 111. Okay. Now let's see, what did I do wrong? This one stays here, and that one's subtracted from 111. That's where I made a mistake.
Maybe you divided.
I think I did, yeah. 1.11 times 10 to the, well, that's basically that value divided by this. I mean, subtract that from it. Okay, now this one divided by that. Is 2.76 times 10 to the fourth milliliters. Okay, do we have 27,000 milliliters there? So that's good. We have to convert it to liters. So liters would just be, move that decimal place 3, so it'd be 10 to the first. Liters, which is 27.6. And that's
D.
yes, D is the closest one. Okay? Clear as mud. So if you stand back and look at the problem, the way the question is asked is, work it backwards.
So to solve this problem, you had to, what did we figure out first? We figured out what?
Okay, where do we need to be? we need to find out what volume to add to this many milliliters of hydrochloric acid to give you the same concentration of hydrogen ions as produced by this part of the equation. So you can't answer this one until you find out what that one is. Right? So that's why we set this one up for acetic acid, to find out what the hydrogen ion concentration is for that solution. Then that tells us what concentration needs to be here for this solution. Okay. And then it was just a matter of definition. Hydrogen ion concentration is moles per liter, it's molar. And you just set it up with your unknown. The question asks, how much do we have to add to? So we add to this to get our volume. Okay. I spent too much time on that one. Maybe we ought to move to chapter 15. Talk about buffers. I need to take a little break.
Okay, yeah, I need a break too. Summer.
Really breathtaking.
Hello? Fine. Now I'm in chemistry class. Oh, wow, okay.
Okay. So chapter 15 is basically about buffers.
All right, thanks, Tanya. Okay. Okay, thanks. Mhm.
So we start with 1 again. All right, so I better specify. Chapter 15. Okay. So, first of all, what do you need? What's the definition of a buffer? It's a solution that changes very little pH. when acid or base is added. Okay? That's a buffer. It doesn't say that the pH stays fixed, constant, with the addition of acid or base. It just says that the pH changes very little with the addition of acid base. So typically what we have when we mix up an acid, a buffer, it's a weak acid.
Website. It's chemistry.
Oh, thank you.
1010, I can find it. 1010, 54, is that it?
Yeah, it should be.
54, 32.
Oh,
34.
I think I put it over.
Yeah.
No, it's not it.
Couldn't find it.
Where are the bookmarks?
I don't know.
Click on that. Yeah. Bookmarks. Bookmark.
Sorry, guys. I'm desperate.
No, do this. No, it's not there.
28, 10, 10. Is it 34, 54? Okay.
Hold on a second. I think I've got it written here.
I'm sorry. I'm in a desperate situation. So sorry. I'm really sorry, guys.
Here it is. It's 54.
Okay, 10, 100, 54, 32,
34. It should be.
slash web, yes. On, that was on or in? It was on.
I think it was on.
Web C, web arc, mainframe CGI.
It should work.
So it's not being found. Jesus help me. Come through, Lord.
Okay.
I'm sorry, guys. I'm really sorry.
What,
But
what
I
is
just I can't really clock it up. Uncle.
yes.
It's an emergency.
Check. Yeah, look over there. Shut that down.
I'm sorry, guys. I don't know what's going on here. We're in a bad state. Well, guess what?
Hey, Sean.
I think it was on yesterday.
There it is.
Thank you so much.
Okay.
Thank you, guys. I was in a state of panic. Thank you. Appreciate you guys. Calculate chemistry.
She's trying to put her portfolio together for promotion. It's due today. So you guys aren't the only ones that wait till the last minute. No, she didn't wait till the last minute. It's just the things huge. I can't believe any promotion committee is going to read that much information. They're not, you know they're not. But they make you do it anyway. Okay, so most buffers, excuse me, are composed of a weak acid, you know, something like that, and its conjugate base. Okay, so that means if this is weak, that means this is strong, conjugate base. And you have a mixture of those two together. So the reaction for the acid reaction is this. Okay? So you have a mixture in there, and we'll talk about the proper concentrations of each one that gives you the best buffer. But for now, let's just assume that there's some of this and some of that in there. So what happens when you add acid? This is at equilibrium, right? It starts at equilibrium. Now, we're going to pull a Le Chatelier on it. What happens if you add acid to this mixture? That's a strong base, isn't it? It's going to pick up most of what you add and convert it to this.
So you're wanting us to say it's going to push it towards the left,
Yes.
what you're looking for there?
So if we add this, it's going to go this way and consume most of what you added. It won't consume all of it. That's why we say the shift is very little. You still have a little bit more of this than you had before, but not much, because this is a strong base derived from a weak acid. Right? So it's going to pick up most of those protons that you add and convert them to this. That means that the pH is not going to shift very much, just a tiny amount. Okay? That's if you add acid. Now, what if you add base? If you add hydroxyls, what is it going to do? Well, hydroxyl is a strong base as well, right? Because it derives from right? So these are weak acids, weak acid, weak base. Acid, well, let's say that's the acid. This is the conjugate base. So the conjugate base of that acid is very strong. So if you add some of this to the solution, what is it going to do? Well, what's the major component in that solution? If it's a weak acid, it's not this one. The major component is this one. Right?
I'll be that way.
We can cancel lab. We would be okay with that.
We'll do this next week.
Yeah, we can just take the rest of the day to study and.
I think I explained it better in the video than I'm doing it now. Probably because I'm distracted.
Yes, I believe you.
But when you add this to the solution, it has two choices. It can react with water, or it can react with hydronium. If it reacts with hydronium, it's going to consume some of the acid, right? If it reacts with this one, then it's going to consume some of that acid. But what's going to happen? What's the response? It's going to shift this way, right? And make up for a large portion of that loss from this strong base. Right? So even in that situation, it's going to maintain the pH.
So adding a base to the acid is going to change the pH.
Right. Neither one will change the pH.
Because it's a weak base.
No, because it's a strong base. I'm almost out. Okay. Let's see what would happen if we skip the lab.
It would be like last semester. Because last semester, the last 12 days of tests.
Oh, just take the test next week and then do the lab after instead of lecture.
Yeah.
Or do a little bit of tiny bit of lecture and then the lab.
Let's see.
Yeah, usually we try to finish just like a couple hours, like an hour and a half of lecture.
Or do the test online?
Or
We
it's
still
just
have-
online.
Oh, we have the lecture and lab. I guess that's another option.
Just a review.
So we had that last semester too. I mean, it's obvious that your face is really hurting. Yeah. But Sarah wouldn't have to miss the lab then too, that's a good thing. I
Oh,
mean,
that is a good point.
I don't know, I'm open to watch it, whatever.
I'm definitely open to it next week.
I definitely am happy to take the rest of the day and go home and watch the video for chapter 15 because I didn't do that yet.
Yeah, and then also work on the lab report that's due next week, the lab next week.
Okay,
Okay, there is that, there's another pro.
so we'll do one final thing here before we part. And we'll derive the Henderson-Hasselbalch equation. Henderson-Hasselbalch is very useful.
What's the name?
There are two names,
Oh, so
Henderson
Henderson
Hassel.
and the person.
Henderson and Hasselbalch.
Bustle.
There's a character that I know whose first name is Henderson. So,
I need to get a refill. I'll be right back.
Okay.
crush up some aspirin there, you know. God, that would be awesome. Because honestly, anything that we show from chapter 15 is just going to go right over my head.
So let's take our generic acid dissociation, and we'll use the simplified version. Rather than reacting with water, we just say it dissociates in solution to produce that. So our K value for this reaction is this expression. Okay? And what Henderson-Hasselbalch, both of them wanted to know was, what's the pH of the solution if you know what these two values are? And you know that one. So they took a cue from Sorensen and used log transformation. So first of all, what we want to do is get the hydrogen ions on one side because we're looking for pH. So we'll get the hydrogen ions on one side, which means this one will go over here multiplied by that one, right? Okay? That one goes up, this one goes down. Okay. Now I'm going to do two things at once here. I'm going to move this one over here and that one over there. And just flip it and take the log of both sides.
Why do you take the log of both sides?
Because we want pH. Actually, the negative log. Right. So I'll write the whole thing out.
Okay.
So here's negative log of Ka And then remember, when we take the log of a product, say this times that, then it's the addition. So we're going to add the negative log of this expression equals the negative log of the hydrogen ion concentration. Okay? Oh, excuse me. That's not right. Oh, wait a minute. Yes, it is. Yes, it is. That's right. This times that. We have to keep this one intact because we don't know what these values are. We usually know what that one is. But what's important here is this ratio. So I'm going to maintain it as a ratio. Okay. Now, let's move over here. So the negative log of Ka is what? Oh, I forgot to flip them. Sorry. I went straight to the negative log. That's okay. Now I'm going to flip and put this one on this side. pH. Negative log of hydrogen ion concentration is pH. So pH is equal to this expression. pKa for negative log of Ka. And then negative log of acid over base. But they didn't like negative here. So we're going to change it to positive. So what happens when you change this to positive? This term flips. Plus log of the conjugate base over its acid.
So it's turning into this formula here on use formulation. pH is equal to pKa plus log of base over acid.
Right. That's Henderson-Hasselbalch.
This is useful because we've done with it.
Right. All you need to know to find the pH is the pKa. Right. If you have the Ka, just take the negative log of it. And then the ratio of these two is the important factor. Okay. Let's go to our titration curve. So you're going to be adding base in the lab next week. So added base.
And that would cause a neutralization reaction, right? As you
Eventually, yeah. But with a weak acid, it goes through a series of changes that are predictable. So this is the pH. And as you add base, you're going to be writing down, say you add so many mils, fraction of a mil, measure the pH. Add some more base, measure the pH. So you get a data set, paired numbers. One, two, three, 4, 5, 6, 7. So for acetic acid, you're going to start out at about I think it's in the neighborhood of 2.8 or 3 right in here. There's nothing but acetic acid in your solution. And then when you start to add base, it goes up pretty quick, like this. Hold on a second. Do a quick calculation. See if I'm on spot. Yeah, about right. So the pH is going to start going up as you add base. You're going to reach a point where it starts to flatten out. At the very most, it's like a gentle slope. This is your buffer region right in here, because the pH is not changing much as you add base, right? And then you get over here, and then it just goes, skyrockets.
So whatever the pH of your base is.
Yeah.
And then
After
just
you
level
neutral.
out.
This point right here, midway through that slope,
Neutralization point.
right? That's neutralization.
When there's just water, there's no really acid or base in there.
Yeah, this is where the total, actually, that's not right. Concentration is not right. Moles of acid equals moles of base.
And that'll be right at 7.
No.
pH of water. Well, that's just where it lines up with on this. pH wise. Unless that was just coincidental.
Oh, yeah. My drawing's not that good. This part right in here is pretty close.
So the number of moles.
Actually, this should be up a little higher. It should be up in this